Hello everyone, welcome to the 4.7 notes. This is called L'Hopital's rule. And just so you guys know, as we do these notes today, this is kind of a one-off topic. This unit as a whole is called contextual applications of differentiation. So this really is not related to related rates at all. And so it's going to feel a little weird. It's going to feel like it's coming out of nowhere, but it really can't come earlier in the units because you need to know how to take derivatives to know how to do these problems. So if you're kind of like, this feels like random and out of place, like totally makes sense. So we're going to go over these right now. So L'Hopital's rule is, and some of this got a little cut off, so I'm going to have to type it in here. But if the limit as x approaches c of f of x produces the indeterminate form 0 over 0 or negative infinity over negative infinity, sorry, it should be negative infinity over negative infinity, or I guess the last one is infinity over infinity. And if the limit as x approaches c of f prime of x equals g prime of x equals L, then the limit as x approaches c of f of x equals g of x equals L. So lots of things there. It will be so much easier as we go through. But you're probably like, no, limits are back. Yes, they are back. But essentially what this is saying is that if the limit of a rational function, so remember this is a rational function, if the limit of the rational function comes out to be 0 over 0 or infinity over infinity or negative infinity over negative infinity, then you can take the derivative of the numerator and you can take the derivative of the denominator. And if a whole number comes out, if a real number comes out, then that real number is also the derivative of the original function before you took the derivative. And so we'll do some example problems here. If you are like, okay, why? There is a reason why. There is a proof. And so if you're interested in knowing the proof, just let me know in class and I'll explain it to you. But we're just going to continue on from there. And so previously when finding limit in indeterminate form, this is what you would do. So right now, like if I were to try to find a limit of this, if I plug in 1 here, I'd have 1 squared minus 1, which is 0. And then I'd have 1 minus 1, which is also 0. And so that's indeterminate form because it's 0 over 0. And so what we would have done in this case is we would have factored. So I would have done the limit as x approaches 1. The numerator factors to x minus 1 to x plus 1. The denominator stays as x minus 1. This is a equation that has a removable discontinuity because this factor right here can technically be removed. And then I'll get the limit as x approaches 1 of x plus 1, and then I can plug in 1 here, and I would get 2. So previously, that is what we did. And for some of you, you're still going to prefer that method, but there's going to be some problems that if you don't use this new rule, you would actually not be able to figure it out. So this is an example that you could use our old method to find the derivative, or you could use the new method, which is L'Hopital's rule. So in L'Hopital's rule, what you'll do is when you figure out, so to use this rule, it has to be indeterminate form. So it has to come out as 0 over 0. If it came out as like 2 over 0, it wouldn't work. But now what we can do is this, what it tells us is this is equal to the limit as x approaches 1 of the derivative of the numerator, which would be 2x, all over the derivative of the denominator, which would be 1. And then I could just plug in 1 into that, which would be 2 times 1 divided by 1, so that doesn't matter, and we would get 2 out as our answer. And so if you see there, that's the same thing. And if we were to go to Desmos, I'm going to graph both of them so you can see kind of what the graphs look like. If it will load, there we go. Okay. So parentheses, x squared minus 1 divided by x minus 1. So here's the original function. As we approach 1, you guys can see, I'm sorry, I'm kind of cutting it. Oh, wait, never mind. You can see that. Okay. As we approach 1, it says undefined, but if you guys look from the left and the right, this approaches 2. And then if I put the derivative in there, that derivative function is just 2x. And if you see here, as it approaches 2 as well. So they're the same thing. So we're going to look first at some examples. I'm also going to add 2 examples right here. And so feel free to look through these. But the question is, does L'Hopital's rule apply? And so don't try to use L'Hopital's rule until you first checked that it actually works. So I'm just adding some additional examples down here. So when I figure out that L'Hopital's rule applies, I'm not going to write equals because you can't equal 0 over 0. And so I'm just going to draw an arrow to kind of test it out. So sine of 0 over 2, 0 squared minus 1. So sine of 0 is 0. and then the denominator goes to -1. So no, I cannot use L'Hopital's rule because this is not 0 over 0. It's 0 over a number. So it does not work there. Let's try the next one. Okay, now I'm going to plug in, this is asking about the limit as x approaches 2. So sine of 2 over 2 squared minus 4. So here's the thing. The denominator goes to 0. I personally don't know what sine of 2 is, but I do know that sine of 2 is not 0. So let's just say, like, I'm going to put a as a number, but the answer is no, because I know that sine of 2 is not 0. And then let's try this last one. So sine of 2 minus 2, that'll be 0. X squared minus 4. Oh, sorry, plug it in. 2 squared minus 4. So this equals 0. This equals 0. So the answer for this one is yes, you can use it because it's indeterminate form. Here's some examples with infinity. So e to the x power, that is an x power, that is an exponent. So e to the x power, think about this as like e to infinity, okay? E is equivalent to, I think, let's look. Maybe I can Google it real quick. E is equivalent to about 2. It is 2.71828. So basically you are going to do sorry, I had to pause it for a second. But so e to infinity is like, it's 2.78. So like 2.78 squared would be like 2.78 times 2.78. E to the infinity would you be doing 2.78 infinity times. Like you'd be multiplying it by itself infinity times. So that's just going to come out to be infinity. And then x squared, well, that's just infinity squared. And that's just going to equal infinity too. Yes, the numerator would grow faster than the denominator. Like that's going to get to infinity so much quicker. I know that's a weird concept, but the denominator also goes to infinity. And so this is an example where you could use indeterminate form. So the answer to this one is yes, because this is considered indeterminate form. And we haven't talked about that being indeterminate form specifically, but now you know it kind of is. This next one, if you plug in, sorry, this should say negative infinity. So if you plug in negative infinity here, you'd have 3 times negative infinity plus 1 all over 4. And so if you did 3 times negative infinity, it would just be negative infinity. If you would add 1, it would still go towards negative infinity. But your denominator would still be 4. And so technically you can't use L'Hopital's rule. But you also don't really like need to use L'Hopital's rule here because it's not indeterminate form. And this answer would just come out to be negative infinity. So the answer to this one is no. But you're not really going to run into a lot of examples like, I guess I would say like that. Like you don't normally get a ton of rational answers like that. So don't worry too much about that. So that's just kind of breakdown. So for all of these from now on, it's telling us to use L'Hopital's rule. So I want you to assume that you can use it, but on the test you might see a question like, could you use L'Hopital's here rule? Or like you might not like necessarily know that you need to use it. So for this one, find the limit as x approaches 0 of 1 minus cosine 2x over 5x. So obviously like 5 times 0 is 0, and then cosine of 2 times 0 is cosine of 0. That's 1, so 1 minus 1 is 0. So indeterminate form. And so what you'll do, so just some more examples, is you will take the derivative of the numerator, and you'll take the derivative of the denominator. This is like, I know that this is a quotient, and it looks like a quotient, but L'Hopital's rule does not like use the quotient rule, unless I guess the numerator itself was a quotient. But don't worry about using the quotient rule for any of these problems. So the derivative of 1 is 0, so that's gone. This, oh, it's back. This is the chain rule because this is composite. The outside function is this like minus cosine, and the inside function is 2x. And so I'm going to start by taking the derivative of the outside function, and that would be, so the minus was already there, but then it would be minus, I'm going to put it in parentheses just to help us. It'd be minus a negative sine, because the derivative of sine is, or the derivative of cosine is negative sine. 2x stays in, and then I have to take the derivative of the inside, which would be 2. So that's the chain rule, it's back. And then the derivative of the denominator is just 5. I'll clean that up real quick for us. So this will be just positive 2 sine of 2x all over 5. And then I'll plug in 0 at this point because it's hopefully going to come out well. So 2 sine of 2 times 0 all over 5 equals 2 sine of 0 all over 5. And this sine of 0 is 0, so this will be 0 over 5, which equals 0. And that's our answer. One other fun fact about this is if you ever take the derivative, so say you were to get to this step here, and say there had been like an x here. So when you had already taken the derivative of the numerator and the denominator, you're using the L'Hopital's rule. But if you had plugged 0 back in here, and you ended up getting 0 over 0 again, one thing that you might have to do is just apply L'Hopital's rule twice. And so if this was your problem, you got 0 over 0 again, just take the derivative twice. And so you can always use L'Hopital's rule like 2 times in a row if you want to. Okay, another example. The limit as x approaches 1 of the natural log of x all over x squared minus 1. Haven't seen this one in a while again, but again, we're just going to assume that it says we use it, so we're just going to use it. I'm not going to test. The derivative of the natural log of x is 1 over x, and the derivative of x squared is 2. I'm just going to plug in 1 here. So the numerator goes to 1, the denominator goes to 2, and so the answer is 1/2. Okay, a couple more problems, and then we're almost done. So the table above gives selected values of a twice differentiable function f of x. Find the limit as x approaches 3 of f of 2x minus 1 divided by x squared minus 9. So I'm just going to go ahead and plug in 3 here to show you like why we need to use L'Hopital's rule. So I guess like right off the bat, you might not recognize you need to use L'Hopital's rule. And so if I didn't know that, I wouldn't just like automatically assume I needed to use it here. So I would have started this problem by plugging in 3. So I would do f of 2 times 3 minus 1 all over 3 squared minus 9. So right off the bat, I'm going to notice that my denominator is going to go to 0. So I'm kind of scared there. And then 2 minus 3 is 6. 6 minus 1 is 5. So I'll have f of 5 on the top. If I go to my table, f of x of 5 is 0. So I have 0 over 0. And so I'm stuck here. And there's not really much else to do except for use L'Hopital's rule. So I'm going to go ahead and use that. So what I'm going to do is I'm going to take the derivative of the numerator and the denominator and see if that helps me find the limit. So let's start with the denominator because it's easier. The derivative of that denominator is 2x. Now, the numerator is a composite function. The inside function is 2x minus 1. The outside function is f of x. So I'll start by taking the derivative of the outside. That would be f prime, keep the inside plugged in, f prime of 2x minus 1, and now I need to take the derivative of the inside, and that is 2. And so, also I messed up. I needed to add right here that limit sign. So that is the derivative part. So I have applied L'Hopital's rule. Let's see if that's all I needed to do. So now I'll plug in 3 in all the places x was. 2 times 3 minus 1 times 2 times 2 times 3. And that's going to equal f prime of 2 times 3 is 6. 6 minus 1 is 5 times 2 all over 6. F prime of 5 based on this table is 7. So I'll have 7 times 2 all over 6 equals 14 divided by 6, which is 7/3. That's your answer. Okay, we got 2 more. So this one is an AP question from a test. It is an FRQ question. And so if you were to plug in 0, that would be the first thing I would try to do, but we're not going to do it for the sake of time. You would get 0 over 0. So now I'm going to try to use L'Hopital's rule. The limit as x approaches 0, so the derivative of e to the x is e to the x. The derivative of a minus cosine is a minus sign, so I'm just going to go ahead and make it sine of x. Derivative of minus 2x is minus 2. Derivative of x squared is 2x minus 2. Now I'm going to plug in 0 and see how this goes. So e to the 0 power plus sine of 0 minus 2 all over 2 times 0 minus 2. Anything to the 0 power is 1. Sine of 0, as we have talked about, is 0 minus 2. 0 minus 2. I have negative 1 over negative 2, which equals positive 1/2. That's our answer. And so, not too bad. If you have felt like, oh, this is so easy at this point, you might not think that anymore as we get to the next problem, because the next problem is humbling. So let's move on and let's look at it. Okay, if you can't see these that well, this is a 2 and this is a 3. So the function f and h are twice differentiable, with h of 2 equaling 4. So if something's twice differentiable, just remember one of the things about differentiability is that it means it's continuous. I don't know if we'll necessarily have to use that there, but that's just a reminder. The function h satisfies h of x equals x squared minus 4 divided by 1 minus f of x cubed, where x cannot equal 2. It is known that the limit as x approaches h of x can be evaluated using L'Hopital's rule. Use limit as x approaches 2 of h of x to find f of 2 and f prime of 2. Show that work leads to your answers. So as you're looking at this, you might be like, what is this? This is impossible. And it is a really hard problem. And so just bear with me as I go through this. But let's just talk about like the main thing that we've learned from this problem and how it connects to what we learned today. And that's saying that this can be used, like finding the limit as h approaches 2, finding the limit as x approaches 2, can be evaluated using L'Hopital's rule. So that means if we try to take this function and we try to find the limit as x approaches 2, we could use the L'Hopital's rule to figure that out. And if we can use it, that means that when we plug in 2, we get 0 over 0. And so that's really important. So if I were to go to take the limit as x approaches 2 of this whole function, x squared minus 4 all over 1 minus f of x cubed, what it's saying by telling me I can use L'Hopital's rule is it's saying this comes out to be 0 over 0, which means when I plug in 2 to the numerator, it comes out to be 0, which that's quite obvious because 2 squared minus 4 is 0, but that means that this is also going to come out to be 0. So when I plug in 2 here into this function that we cube, it's going to come out to be 0. And so I'm going to solve for that. So I'm going to add this to both sides. And I'll get 1 equals f of 2 cubed. And then I got to solve for f of 2, so I'll just take the cubed root of both sides. And I'll get 1 equals f of 2. So I've solved half the problem so far. I have figured out that 1 equals f of 2. And I did that from that little fancy rule that told me L'Hopital's rule. That said I could use L'Hopital's rule. Now we have to find f prime of 2. And I don't have any derivatives here, so that means I probably need to take some derivatives. And using L'Hopital's rule, I know that, based on everything I've learned, that the limit of this at 2 is equal to the derivative of the numerator and the derivative of the denominator at 2. So that's what I'm going to do next. I'm going to take the limit of the numerator. And so the two functions aren't equal, but their limits are equal. So the derivative of the numerator would be 2x. And the derivative of the denominator, the derivative 1 is gone. This beautiful thing is the composite, because f of x is the inside, and then technically that minus 1 is outside, and then the 3 is outside too. So I'll take the derivative of that. So that would be minus 3 f of x squared. So that's like the derivative of the outside with the inside plugged in, times f prime of x. And here, up here, it tells us, it's getting so confusing here, but there's like a couple other things it tells us. It tells us that h of 2 equals 4, okay? And this is, you're going to be like, what are you talking about? And you know what, just stick with me here. But it says h of 2 equals 4, okay? Now, it also says that this function is differentiable. And like I said earlier, if a function is differentiable, it is also continuous. And if a function is continuous, there are 3 conditions that are true. The limit exists. The point exists. And finally, the limit equals the point. And so this right here, this information right here is saying that h of 2 equals 4, which means the limit as h approaches 2 also has to be 4. And so this expression, based on L'Hopital's rule, when I plug in 2 here, I should get out 4. Because if the point is 4 at 2, then, and it's continuous, the limit has to be 4 at 2. So what I'm going to do from here is I'm going to plug in 2 into this function. And I'm going to set that equal to 4 because that's what our limit's going to be. 2 times 2 is 4. Negative 3. So f of 2, based on what I found out earlier, f of 2 is 1. It'll be 1 squared times f prime of 2. That's what we don't know. That's what we're trying to figure out. That all equals 4. So my end goal is to find this. I'm going to need a little bit more space. I'm going to multiply to get this off the denominator. I'm going to multiply. So this will simplify to negative 3. But I'm going to multiply negative 3 times f prime of 2 on both sides to get that to cancel out. So now I have 4 equals 4 times negative 3 is negative 12 times f prime of 2. Ignore this. Divide negative 12 on both sides. And I'll get negative 1/3 equals f prime of 2. And now I'm done. I found all the information I needed. So this is a really, really hard FRQ because there is so much stuff that you have to connect in this problem. Like things from like literally every single unit this year. But I'm hoping you enjoyed it. So thanks for watching this video. Let me know if you have any questions.